No, 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 no.
A complex relationship between water speciation
Speciation.
and hydrogen isotopes with composition in silicate
Jeez.
metals. Water speciation. The directors always
Actually doing stuff is really cool.
this use of numbers from Egyptian times to the modern but along with tell me your name and how you hope you and so I translated it to Spanish, so it took me all weekend to do it because it's a complex and now it's there. It's interesting. I compare Google Translate between now and what it was like 4 years ago. It reads day and night. As a matter of fact, I found that in one translation I gave to translate, I only had to change like 2 or 3 things. It was so good. And in the other translation I noticed that it lacks the focus. Because a global focus for, is this for personal or for formal? Do you instead get it? And so it doesn't have that global focus to try to get a uniform translation. I'm curious. Eventually,
Oh, they can't even listen to the weather anymore. It's super sticky.
Hey, so thank you everybody for joining us on this beautiful Monday morning. I hope you had a great weekend. Just about a week and a half, maybe 2 weeks ago, Michelle said, oh, we don't have a speaker for this Monday. And I just leaped at the opportunity to inform you all you good people, about the cool things that we do up on the second floor. And actually, I was inspired to do this because not once, but twice in the last, I'd say, 3 to 6 months, I had mentioned what cool things are going on with water and silicate melts, and 2 people said, don't we know everything about that? I mean, isn't that completely known? And it turns out it isn't, and so I'm going to try to convince you that in this talk. I mean, everybody knows why. Oh, by the way, I'm George Cody. Oh, thanks, yeah. Right, right, right. So I was born 57 years ago in a small village outside of Princeton. Now, I took a rather windy, convoluted path to this fantastic laboratory, but I've made the best of it since I've been here. I think that's the best introduction I can give. So everybody understands why water is important. So if water solubility and solubility mechanisms are critical, water is the principal reason we have melts. It suppresses the solidus. It creates melts within the Earth. Profoundly affects the density of melts, so basically changing the buoyancy characteristics, allowing melts to rise to the surface. And it affects, to the tune of many orders of magnitude, the viscosity of the melt. So it's critical for basically the major means of energy and mass transfer in the upper mantle, at least, and the lower crust. And it can affect the nature of volcanic eruption. So it's one of the factors that controls whether an eruption is explosive or smooth and effusive. Right. So as I said, surely we know everything about water and silicate melts. This has been studied substantially, at least 40 years, probably more like 80 years. And the answer is actually we don't. We still don't know how and why water interacts the way it does with silicate melts. We understand that melt composition matters, but we don't really clear it. We can't tell you exactly why that's the case. We understand that water content matters, but we can't really tell you exactly why that's the case. It's largely empirical. And we're only now gaining information critical to understand the importance of water in silicate melts. So what I'm hoping to convince you in this talk that I would say we know more now than we ever did, but what we've learned in recent years is actually it shows how confusing the system actually can be. So how I got involved in melts, I'm an organic geochemist. This talk, I should tell you as a background, I was invited, I wanted to give a talk at ETH. I had a former postdoc he's a faculty position there. And I told him, you've got to invite me to ETH because I've never been there and I want to go give a departmental seminar like this one. And I know Peter Ulmer and Max Schmidt, and even though I'm an organic geochemist and these are these ultra high pressure people, we like each other. And so they kept trying to find a time to come when they would be there. And we never could seem to find this. And finally, Peter Ulmer said, well, you know what? Why don't you give the plenary lecture at the Experimental Petrology Conference? And so I said, okay. And he introduced me. He goes, here's George Cody. He'll be giving a plenary lecture in this Experimental Petrology Conference. He's an organic geochemist, and he's going to be talking about silicate melts. But where I'm going with this is that it turns out because I've been running the Geophysical Laboratory Carnegie solid-state NMR facility, I have been collaborating very closely with Bjorn Meesen and many of his students and postdocs, and Dionysius Fustouskas as well, on using NMR to understand melts as quenched to glasses, right? So we have to do this solid state. And so I now have actually quite a few first author papers in experimental petrology, at least the analytical end of things, and I know quite a bit about this. So I was able to give a very credible talk to this very esteemed audience. And I will cut to the conclusion of my talk. I asked one of the people who had been a former postdoc here, her name is Monica Koch-Mueller. I don't know if you remember her at all. She was a postdoc here probably 15 years ago. And I asked her what she thought about the talk, and she said, well, I learned two things. She said, I learned that you're very, very enthusiastic, and that melts are very, very complicated. And I said, well, that's it. So that was the essence of it. And that's what I took that talk and sort of put it together here and then added some things to it to make it a little bit fresher. So the bottom line is the technique that I use is solid-state nuclear magnetic resonance spectroscopy, and the joke is that NMR stands for nothing much really. And what it does is it provides a very unique view of very, very complicated systems. So here we're looking at water melt interactions as quenched to glasses. So throughout this talk, the prevailing assumption is that the structure of a glass is the structure of the liquid at the glass transition, because we can't do solid-state NMR on liquids. And then I'll talk a little bit about unexpected hydrogen isotope issues that may have broad geochemical significance. So there is our NMR, and there's Hikaru Yabuta. And I have some very good news. If you haven't heard it, she is now an associate professor at Hiroshima University, which is critical in the Japanese system. So she has been stuck at assistant level at Osaka University for a very long time. And now she's made that critical bridge and is on her way. And kudos to her, because she really has been working hard. So it's nice to say that she's on her way. There she is, smiling. Most of the elements in the periodic table have isotopes that are NMR active, so every one of these is in color, is got an isotope that has spin, so which means we can do NMR on it. And in our laboratory here on campus, we've done used quite a few different isotopes to study things. So for example, in silicate studies with Bjorn and postdocs, we've used all of these isotopes in black, and we're interested in using the two isotopes that are in blue to say some interesting things about melt structure, and so on and so forth, in paleontology, climatology, geochemistry, cosmochemistry, geobiology, solid-state chemistry, working with Tim Strobel and others. Very, very versatile tool, actually. It's not common in geofacilities, but I think it really ought to be. I can't think of it's as useful a spectroscopy as any on this campus with regards to a lot of the questions that we ask. For those of you who don't do NMR, there's some very annoying aspects of it, and I'll just highlight some of them to start. First of all, the frequency increases from right to left, and that's a little bit odd. And moreover, the frequency is not listed in frequency that you depreciate, it's in ppm. What it is it's a radio frequency spectrum, but we reference it to a standard, and we refer to the energy as parts per million frequency shifts off of the standard carrier frequency. So we define something as 0. So it's a little disconcerting because you'll see in some cases negative frequencies, which don't make a lot of sense, but that just simply means they're negative relative to an arbitrary standard that we choose to be 0. And then the last bit is an isotope, a specific emission-based spectroscopy, and the beauty of that is there's no interference. So you only see what you're looking for, right? And it's in contrast if you were doing, say, infrared absorption spectroscopy. You're going to see every single vibrational mode you have. Here, if you're looking for hydrogen, you only see hydrogen. If you're looking for deuterium, you only see deuterium, even in mixed systems. So it's really has and you could, consequently, we've detected things down to parts per million level. I wouldn't say without difficulty, but we can do it. So the nuts and bolts for this particular talk is largely based on work that Charles Lalas was doing here before he left. And Bjorn Meesen likes to work on these very simple, so-called simple systems. I'll show you they're not simple at all. And the reason being that in a so-called simple system, you get a better handle on seeing what's actually going on. If you go for full chemical complexity associated with a basalt or a rhyolite or rocks of other compositions when melted, there's so many things going on in those systems, it's very difficult to extract the details. So classically, Bjorn and myself, working with Bjorn, has worked with this system, the sodium tetrasilicate system called NS4. And we thought it would be interesting. We talked to Charles. He said, we really haven't explored the effect of alkalis, strangely enough. You'd think this had been done to death, but it had never been done before since Charles got here. So I said, let's just look at what lithium and potassium do, because we had seen some interesting things going on with the sodium. And so Charles very carefully synthesized a suite of glasses that were hydrated at 3, 10, and 17 mole % water. So the capacity of these melts to suck up water is really quite substantial. And then he did this in a piston cylinder apparatus. So getting back to the spectroscopy that I do, I almost feel like I keep showing the slide over and over again because I'm the only person here who does NMR, so I can always reintroduce it, I suspect. But the good bit is it's an isotope-specific emission spectroscopy, so again, you only see what you look for, no interference whatsoever. That means I can do, as I'll show you, silicon-29 with 17 mole % hydrogen. There's no effect. You only see what you're looking for. The bad is the signal is very weak, and so it takes a lot of time. And then the ugly, or you might say it's the beauty, is NMR physics is very complicated. So it's exactly grounded in quantum mechanics, and that's just the nature of things. So in this particular talk, I'm going to focus about hydrogen NMR, deuterium NMR, and silicon-29 NMR. And then the only heads up here is that these two spectroscopies are what we call spin-half systems of one energy, two-level, one energy spectrum, which is relatively simple. And then deuterons are a spin 1, so it's a two-level system, and it's a little bit more complicated. Okay, so these are silicon-29 NMR spectra of various tetrasilicate glasses. And I'm going to apologize. I tried my very best to keep the color scheme the same, but at a certain point, I just went off the rails. And I'll show you when that happens. I think it's obvious, but I thought this would be really helpful. In any case, so what you're looking at is just the silicon-29 environments, and there are different types of environments that you'll find. So the silicon is always in these particular low pressure melts, it's always tetrahedrally coordinated. If it's coordinated to 4 other silicon tetrahedra, we call it a Q4. If it's got only 3 coordinated silicon tetrahedra around it, but then one we call non-bonding or non-bridging oxygen, we call it Q3. And if there's 2 non-bridging oxygens, we call that Q2. Ultimately, you go to Q0, you have no bridging oxygens. And you see, so lithium, you see there's distinct differences. And I should tell you that the presumption is, and it's a correct presumption, that in a dry system, the lithium oxide, sodium oxide, potassium oxide goes into the melt and depolymerizes the melt. There's no free lithium oxide. It just goes in there and it depolymerizes the melt. So the degree of melt depolymerization between the red, the black, and the blue are identical stoichiometrically. But obviously the spectra are not. And you see a couple different things. One, you only see Q2 with lithium. You see, and these are basically normalized based on their integral. And it looks like you've got more Q4 than you do with sodium, and it looks like you've got less Q4 with potassium. It turns out what's happening is you can see, is the peaks are moving. So now when you add 17 mole percent water, you see that this Q4, which is the highly polymerized species, dives, right? So clearly you're seeing the water is going in there and it's doing something. You still see the same frequency shift of the Q4. You had an opposite frequency shift of the Q3 here dry. You don't have anything there now. And the Q2 that was here in lithium is now gone. So just these very simple systems show you that things are very complicated. Now, what that shift means for the Q4 is interesting. That's the lithium, that's the sodium, and that's potassium. And what it means is when the alkali goes in there, it changes the mean silicon bond angles. And it's almost as if the nature of the alkali is actually compressing the silicate components of the melt in a very interesting way. And the reasonable question is, why is that happening? And we have absolutely no clue. This is just one of the first of many things that I could tell you that the NMR can clearly show you that we don't have an answer for. But it's a very large effect, and it's pretty cool. As I showed you, this is from Charles Lalas' paper in Geochemical Perspective Letters. And he had a clever way of just subtracting the wet from the dry glasses and showing you in the different spectra that you can see the degree of polymerization, the change in the Q speciation. But what you also see here is that the magnitude of depolymerization is greater for potassium than it is for lithium, and sodium sits in the middle. So that's interesting, and we don't quite understand that. So, as I said, these sodium tetrasilicate glasses, or any of these tetrasilicate glasses, are in principle very simple systems. And the dissolution of water, I said, well, isn't that well known? Hasn't that been studied for 50 years? And the answer is yes. And don't we know exactly what's going on? And to a superficial sense, we do. Water does one of 2 things. It either goes into a melt and stays as H2O, or it hydrolyzes this ether to form 2 silanol groups, and that's it. And so you might intuitively think that that's all you're going to see then is 2 different peaks corresponding to those 2 different species. But it turns out that's not what the hydrogen NMR spectrum shows. First of all, it turns out the hydrogen NMR spectrum cannot distinguish between a hydrogen bonded to a hydroxyl in this case, or a hydrogen bonded to a silanol. That's not what's being measured here. So, similarly, when you look at this, you see a lot of sites. There's many, many different peaks and shoulders and whatnot. If you were to fit this spectrum, even though the sodium tetrasilicate is very simple, the hydrogen NMR spectrum is actually fairly complicated. So it tells us that speciation is much more complex than water or silanol abundance. I've already told you that you can't distinguish these 2 species. And so what are you measuring? You are measuring distance. So the hydrogen NMR spectrum in this particular case is a distance spectrum. So, for example, this predominant peak, and this is a correlation of probably 150 different compounds that relate hydrogen frequency to the oxygen-oxygen distance. And you can't, that's done with crystallography, right? So you can do that with extraordinary precision. You can't see hydrogen in crystallography, but we know what happens when 2 oxygens come together. So you have a hydroxyl and another oxygen. The lone pair of electrons of that other oxygen will start to interact with the proton and will pull the proton away from the oxygen. And so what you're looking at is basically a measure of the oxygen-hydrogen distance measured indirectly from the oxygen-oxygen distance. And so you see this peak here corresponds to a fairly short distance in picometers, and this peak here is a much longer distance between the two oxygens, and everything in between spans everything in between. So it's a very, very, very sensitive ruler, if you will. And that's something, typically when we do NMR, we're always thinking about NMR revealing the intricacies of the chemistry, but actually what you're seeing here is simply what I just described to you, just oxygen-hydrogen distance. So this is the hydrogen NMR spectrum of these tetrasilicate glasses, and so we have 3, 10, and 17 mole percent, and so you can see the intensity increasing here. And you'll see something really quite remarkable. So I'm highlighting these two peaks that I showed you previously that correspond to two different distances there, so red and blue. Here you have your red and blue. And what you see is lithium, the hydrogen also clearly goes into sites that have basically relatively large volume and presumably saturate those sites and then start to fill into other sites that have smaller volume. In potassium, you see the complete opposite. And what struck me about this was, had I not known this before, if I hadn't started with sodium tetrasilicate, I would have reasonably assumed that this would have a single peak somewhere in the middle. But it doesn't. It has basically both environments with essentially nothing in the middle. We have no idea why this is the case. This is something that we just observed 2 years ago, and I think it's pretty damn interesting. So here's another case where, yes, we know basically what water is doing, but we don't know exactly why it's doing it or how it's doing it. So that's hydrogen NMR. And as I told you, basically large volume sites, and when I say volume, I know I'm talking about distance, but you think about it as basically a distance corresponding to a volume that the hydrogen finds itself in. So lithium has these large volume sites, potassium. As I said, I would have expected the sodium to produce some sort of site intermediate between the two, but it doesn't. It gives both lithium-like and potassium-like hydrogen sites with fairly, not exactly equal abundance population there. And you'll note that there's a little something over here. I will highlight that later. That's pretty interesting. So bottom line is we do not know why. So it turns out that one of the interactions, so what we have to do in the solid state is we spin our samples as fast as we can spin them. In the case of hydrogen NMR, and we do this for two reasons. One, we're trying to average out what's called chemical shielding anisotropy, which in the case of hydrogen NMR is essentially nothing, so we don't have to worry about that. But what we do have to worry about is that the magnetic moment of a proton is as large as you'll find across the entire periodic table. It is, tritium is actually larger, but it's radioactive, so we don't work with tritium. So it's the strongest magnetic moment, and it will couple with itself and introduce what's called dipolar broadening and dipolar splitting. And what will happen is, the faster we spin, the weaker the dipolar interaction gets. But it turns out the dipolar interaction for water molecule, two hydrogens on a water molecule, is about 50 kilohertz. And the fastest I can spin these samples currently is 22 kilohertz. So we're going to have residual signal from the dipolar interaction that we can't get rid of. And that's seen here. This is a theoretical calculation, but it's an exact calculation of the, it's an exact quantum mechanical calculation of a rigid water molecule being spun at 22 kilohertz at the field, the frequency of our magnetic field up in the lab. And so you see these side bands, and their intensity is proportional to the water content. So I told you that we can't distinguish between silanols and water spectroscopically based on sort of a primary spectroscopic feature, but we can with the intensity of the sidebands, because a silanol will have no sidebands. Only the water molecules will produce sidebands. The silanol is partly because the dipolar interaction, or the scales, is 1 over r cubed, so it decays very, very quickly. And so two hydrogens have to be very close together. And just as an example of this is a hydrogen NMR spectrum of gypsum, and you see very intense spinning sidebands. And so we thought, well, this is great. We've got this nice, so this is the central peak, and the sidebands, if there were sidebands, would be just outside the spectral window, so you can't see them. So we thought this would be a nice measure to say something about what water's doing in terms of these different systems. And when we do that, so we just expand these out, and you can see that there's At very low water content, there's just a teeny tiny little hint of a sideband, and as water content increases, clearly see sidebands. So for lithium tetrasilicate, we see definitely there's some water here. Sodium, definitely there's some water here. And in potassium, there's almost nothing. There's just a little tiny bump there. So very, very little dipolar interactions exhibited in the potassium. Now, I've already shown you that it's more depolymerized, which is what you would say. In this case, it looks extensively more depolymerized. And I should tell you, again, we can make these observations, but I'm not even going to offer you at this point a speculation. I'm simply telling you that, again, countering the idea that we know everything that we need to know about water and silicate melts, the answer is simply no, we don't. And then it gets worse, as you'll see. So Charles Lalasque did a similar analysis, and the way that people have attempted to get a handle on the speciation of a silanol group versus a water is using these tiny, tiny, tiny little, they're called sum bands in the infrared spectrum. They sit below, well, actually higher energy than the primary vibrational mode of the hydroxyl, right? So these are these little tiny, tiny things, and they've been described to silanol and to water. And so they take the ratio of these two, and you can determine the molecular water content. And so he said, well, if the NMR is correct, we should have a nice correlation between the sideband intensity and the ratio that we measure with the FTIR. You can see it's a very nice correlation. So clearly, the NMR makes sense. The FTIR is what it is. It's the classic way to do things. These tiny little bands, they're almost impossible to see with a thin section that's thin enough to get infrared light through the primary vibrational modes. So typically, you'll make, that would be on the order of 20 microns or so or less. For these, to measure these, you have to use a 100 micron thick section so that you can actually see them at all. I mean, their absorption is absolutely tiny. And again, they, quote, define OH and H2O, and they certainly seem to vary systematically with water content, right? So here you see the hydroxyl seems to be quite intense here, and then as you add more, the water gets more intense there. And it does, you know, it's one of these things where if it worked well, wouldn't it be lovely, you know, because this is something that's the only way that we know, aside from NMR, to do this. However, Charles showed that the FTIR is not at all simple or straightforward. It works really well for very simple systems, like the lithium system. It gets a little bit in trouble with the sodium, and by the time you get to potassium, everything gets smeared out, and it's very, very, very difficult to really assess what's going on there. And so if you start applying this to an actual rock composition that has potassium and sodium in abundance, like a rhyolite, you know, what are you going to see and how are you going to interpret it? If it's a mixture between these two things can get pretty sticky. So Charles was very careful about this paper because this is the classic work of Ed Stolper, and you don't want to be getting people upset at you, particularly when you're young in your career. But he published this and said, look, this is not simple. So this is the canonical view out of Ed Stolper's early work in the 80s and subsequent students. And this is this is Lynn and Stolper 1990, I think. And it's a really great paper. And the idea is that they predict that in all of these different systems and measure using this FTIR, that silanol, as you add water to the system, so XB is the fraction of water if you're adding a system, so it's increasing from left to right. Initially, the water all comes in as silanol, you're depolymerizing the melt structure. That saturates, and then the content of just molecular water grows and grows and grows and grows until you hit the solubility limit of the system. And so this basically defines the thermodynamics of the water-silicate interactions, and it doesn't vary significantly across a wide range of compositions. So this is the canonical view, and I will jump ahead. Bjorn Meesen is currently working on the third version of the silicate book, and I took him aside a couple weeks ago and I said, you know, Bjorn, you might want to put a little wiggle room in that chapter about water and silicate melts, because when we do the same analysis, our analysis using the hydrogen NMR, we can determine OH and H2O, assuming that only H2O will give us a spinning sideband, and silanols won't. So we do that with either gypsum as a standard or our exact calculation. This is what we see with lithium. Silanols in blue and molecular water is in black, and we just simply see with increasing water content, both of them increase. And then in the sodium tetrasilicate, you see a slightly enhanced increase by the slope of the silanol but an also progressive increase in the H2O. But when you get to potassium tetrasilicate, basically it's all going in as silanol, which is absolutely consistent with what the silicon-29 NMR showed us, right? And the simple lack of sidebands. So there's a little bit of molecular water towards the end, but that's about it. Now, just before he left, literally this data is just fresh out there. Mike Ackerson is working on these hydrated rhyolites, and he told me, by the way, I could show this. He's showing this currently in Japan. So these are the experiments we did with Charles Halas. Now, this is a rhyolite composition, and it shows similar sort of behavior, but again, where the silanol is dominant. Yeah?
Sorry.
Yeah.
How does this x-axis scale here compare to what you showed on the previous plot?
Yeah. I'll show you the next. Let me show you the next one, because that'll be so. So here it's the same idea, but at weight percent. Yeah, they were using XB in their. I don't know why they did that, but I wanted that one figure to show that everything overlaid. And some people use mole, and some people use weight percent. It's annoying. I like mole percent. I don't think well in weight percents, other than. So in any case, we're comparing now rhyolitic glass and a rhyolitic glass. This is Silver and Stolper, 1990. They're making these measurements. They're beautiful measurements. There's no denying that they're measuring what they're measuring. And they have a very nice solution model that would give you this behavior that makes physical sense, right? So they're not. These are really sharp people. This is also rhyolitic glass, and this is what we're seeing. And so Mike is a little nervous about this because he's like, I don't know if I want to write this paper. And I said, well, you got to write it very, very carefully, right? And you simply have to say, look, we have issues. Maybe there is an NMR issue, so we've got lots more experiments to do. Or maybe this is an FTIR issue, in which case we have to sort that out. I will say that the physics of the NMR is extremely straightforward, whereas the physics of the so-called combination bands is not at all straightforward. So you can't really, and I don't know, I have my bias because I do NMR, right? So, but for sure we need to reconcile this inconsistency, and we're working on that. So that's pretty startling, isn't it? I was pretty amazed. Mike was like, wow, this is incredible. So how about the deuterium NMR? This is something actually is an outgrowth of, again, one of the nice things about being here is that we have postdoctoral fellows who come and go. And when they come, they always bring something to the problems you're working on in the laboratory that you're in. And I had a postdoc, Ying Wang, who's absolutely just wonderful. And she came here and she wanted to do deuterium solid-state NMR at natural abundance. And I told her that's impossible because there's just not enough deuterons. But deuterium NMR is straightforward. But I never normally would do that because why would I do deuterium NMR if I can do hydrogen NMR? And I can do hydrogen NMR very easily. Part of the problem with deuterium NMR is deuterons are spin 1. So they have 2 energy level differences versus a 1 energy level difference for spin half. And then the quadrupolar interaction splits those 2 energy levels so that you get a very strange looking line shape. So for 1 deuteron in 1 environment, you get what's called a Pake powder pattern. And it's an overlapping of 2 radial powder patterns in this classic way. And so the magnitude of the quadrupolar interaction is related to the distance, energy distance between these 2 peaks. And it's just this additional complexity. And I'll show you how it manifests itself in these so-called simple glasses. So what happens is we're spinning these things at about, here I think I'm spinning them at 8 kilohertz. And what you're seeing is that Pake powder pattern will break up into a series of what we call rotational echoes, or sidebands, spinning sidebands, where the difference between each one of these peaks is exactly the spinning speed. So it's exactly 8 kilohertz from part to part. So if I didn't spin it, you'd get a solid line shape that looked like that. Imagine this is all filled in. You wouldn't see 2 things crossing each other like that, but you'd see. And then when you spin it, you clearly see the 2 peaks. This is a glass, so the hydrogen is going to be, deuterons are going to be in a bunch of different environments, so it's going to be broadened a little bit, right? But you can clearly see, we would call this the classic Pake powder pattern. And so you can see why would I want to do deuterium NMR? I mean, it doesn't tell me anything that I didn't already know, and in fact, it gets more difficult to extract some of the information I would like to have because it's difficult to pull out the isotropic features. So Now here's the sodium tetrasilicate. And it also, you see the two peaks here. And I would argue it's not quite classical, but as I was saying to somebody, I said, the differences are really subtle, and so you probably wouldn't worry about it too much. Now, I don't know if you can see this back there. There is something cool with this. You can kind of see what's going on in the system, but you'll really see it with the lithium. So there is actually a pattern lurking below this pattern, and if you imagine it, you might see something sort of almost like an interference fringe. So we did the lithium, and we're like, what? So what I was getting at is you might see that pattern kind of hidden like that. And it turns out, if you imagine it, it's there. It really is there. I'm not going to show you the slide, but it is there. So I told you sodium has these two sites, potassium has the one site, and the lithium has predominantly the other site. And that other site, the lithium site, has got a completely non-classical shape. But it's a shape that's very well known in deuterium solid-state NMR. It also has this very, very sharp peak. Turns out that peak has no spinning sidebands whatsoever, which means that that deuteron is so mobile that it's actually able to average out the quadrupolar interaction to zero, which is physically impossible for us to do with any spinning speed. I mean, we're talking 250 kilohertz or so. So it clearly has something that's extremely mobile and liquid-like, even though these are solid glass. And then this line shape is totally characteristic with some sort of motion that modulates the quadrupolar interaction. So it has some restricted mobility, but the water or hydroxyl is able to sort of wag and flip. And then down here in the grass, literally looks like on the grass, you've got a very rigid frozen deuteron, which has a very high frequency and a large quadrupolar interaction extending way out here. So this turned out to be pretty cool. And we thought to ourselves, so if you recall, the lithium hits on this one site with a large volume, and the potassium, all the hydrogen seems to be in this little tight volume. And so the fact that the water or solanol tends to be very rigid in the potassium system and very relatively mobile in the lithium system is consistent with that. And in this business, I love consistency, right? So I can find this correlates with that, and that's... So, as I said, wide-line NMR is typically kind of boring, unless you're interested in one thing, which is molecular dynamics. It's very, very useful for molecular dynamics. And that's not something that I've been doing in the 22 years I've been here. I've focused on basically condensed solids where dynamics is an issue. And now all of a sudden we have a pretty cool system. So in principle, we should be able to model that line shape. And if it was an important thing to do, or for some reason you needed to do it, we could actually measure. Now, well, this is sort of a kind of funny story about data that it was collected and never really analyzed. We used to have a postdoc here who went off to NIST to work at their neutron facility. It's a really nice one. He was doing neutron inelastic spectroscopy. And so we gave him some hydrated systems, because one thing that neutrons interact with strongly is hydrogen, right? It's like lead is to X-rays as hydrogen is to neutrons. And so he went off with hydrated sodium silicate glasses, and we never heard about it. And I saw him like 2 years later, and I said, well, I guess that was a really bad sampling. He goes, no, it was really interesting. I just got really busy, and I put the data off to the side. And then he disappeared completely. And so we have this tantalizing set of data somewhere that probably would have enabled us to anticipate this sort of duality in terms of the relative mobility of hydrogen in different environments in the system. So maybe we don't need the data anymore, but if you wanted to, you could confirm it. So the bottom line is what I just told you, and now the trick is, I said, if you could do deuterium NMR like you do hydrogen NMR, in other words, is there a way to get rid of the quadrupolar interaction or hide it such that you can really do a direct comparison with hydrogen NMR? They should look, in principle, exactly the same. And so the question you might argue is, why in the world do it? Well, we did do it, and they don't look the same, which turned out to be a really amazing discovery. So it turns out there's a lot of tricks you can play in NMR, and if you look at the classic textbooks, they talk about sorcery in NMR and exercising the evil in NMR. I'll show you if you don't believe me. It's just the way people tend to look at it. But there are a lot of tricks you can play, and so there really is a way, and this is an exact simulation now, a way of basically hiding the quadrupolar interaction and extracting a purely isotropic spectrum. And I won't bore you with the details of how it's done. Well, I sort of do up here. So if you're interested, it's just synchronous, very highly synchronized, spinning with a very synchronized, with a very narrowly defined spectral window. So here's a simulation where you have two different deuterons in two different environments. So one has a weaker quadrupolar interaction, and the other one has a larger quadrupolar interaction. Exactly the same things, and they have different chemical shifts. And when we do this magic, we extract exactly two isotropic peaks. So now we can do this with our systems and compare hydrogen with deuterium. And so this is what the deuterium, isotropic view of deuterium looks like for lithium, sodium, and potassium tetrasilicate. And if you recall, you see more or less the same thing as what you expected, right? So the lithium, you get mostly this blue, large volume site. You have some of this red. Sodium, it tips over. Now you've got much more of the deuterons are in this, low volume, high frequency site. There's a little bit in the large volume, low frequency site. And then potassium is skewed very, very strongly towards this one site. And then you see this other peak here, high yellow, that's doing something interesting along this path. And so I'm almost at the point where my color scheme started to bulk. So the bottom line is, so as expected, they do look very similar. But I said what you won't see, but if you looked at this closely, well, first of all, you can see the intensity of this extremely mobile deuteron was, by the way, turns out to be that peak right there. Is very, relatively speaking, very intense. It's not a lot of it, but it's very sharp and very intense and very prominent in the lithium, and it decays very, very quickly with composition down to very, essentially just a blip in the potassium. So that's fascinating. And then the other thing that's harder to see, but I'll show you in a second, is that there's a consistent, across each of the alkalis, a preference of the deuteron for the low molar volume sites relative to the hydrogen volume sites. And this is consistent, and we had seen this in sodium tetrasilicate, and so it was interesting to see it here. So here what we'll do is we'll compare. Now here's where my color scheme started to fail me, but you get the idea. The most intense one is 17 mole%, whether it's black or blue. So red or blue. But yeah, so again, we're seeing the same things, and you see this very interesting relationship. So there's a little bit of the sharp peak here in the hydrogen NMR spectrum. So whatever this is, hydrogen finds itself in that environment. But for whatever reason, the deuterons really, really want to go into this environment. So the relative intensity difference between, at 17 mole%, between this peak here and that peak there is startling. And we hadn't seen that before. And it actually speaks to a mechanism that we had proposed, but really didn't have any evidence for, direct evidence for, which was that it would indicate potentially a different solution mechanism than just a simple hydrolysis. And the idea is that if you had a lithium non-bridging oxygen to a silica, the deuteron could come in there and free lithium OD, lithium OH or lithium OD, and a deuterated silanol there. So, and this is clearly favored at high water content, and you see the same thing in the water, but it's definitely that's favored at lower water content, relatively speaking. So this solution mechanism is probably the most sensitive mechanism that we've seen with distinguishing a deuteron from a hydrogen. And so the ratio of lithium OD to lithium OH is extremely strongly dependent on water content, which is really interesting and might even be important. So when we go to the sodium tetrasilicates, again, you see this preponderance. Now you clearly see that the deuterons given a choice would prefer to be in this site, and whereas the hydrogen would prefer to be in that site. And you still see this sodium equivalent of sodium OD there and sodium OH there, but it's much, much weaker than what you saw with the lithium. And then further and so on and so forth for potassium. You see, again, there's not a lot of water relative to this site, but if it can put water in this larger volume site, it will do so and differentially. So you're seeing this intermolecular isotope fractionation effect that we had discovered in sodium tetrasilicate. Now we see it in these different systems. And so the bottom line is with sodium versus deuterium, again, you see most obvious in this system, intermolecular fractionation. Again, you see this dissolution mechanism, but it's much, much weaker. Potassium is weaker still. And then Charles did a nice plot where he liked to think about the alkalis in terms of their ionic radii. So this would be lithium, that would be sodium, that would be potassium. And he looked at the effects of this isotope fraction, if you will, an intermolecular isotope fractionation between the high frequency peak and he called it the medium frequency peak. And you can see that there clearly is a relationship between water content, right? So 3 mole percent fractionation is very large. At 17 mole percent, it drops quite precipitously. But then you also see superimposed on that a very strong cation effect. And so this is pretty interesting stuff. So, good, I'm almost done. So why would this be important? Well, there's a lot of thinking and interest going on in the discovery of reservoirs, if you will, of water deep in the mantle. How much water is in the mantle? How would we know? How did it get there? How did it stay there? The presumption is that it probably got there at the magma ocean phase of Earth's history, because it turns out it's very difficult to extract all the water out of a melt that's crystallizing, because water loves to be in a melt. One thing we know for sure is that isotopically, in terms of deuterium abundance, that when one does detect water not only in hydrous mantle minerals, they tend to be depleted relative to the oceans. And nobody's really put forth, in my view, a reasonable explanation why. So the simple cartoon here is if you have a hypothetical crystal water phase diagram, and you stay way up here in temperature, some composition, say here you've got melt and water, and you start to crystallize, and at a certain point you're going to intersect the liquidus, or there, and you start to crystallize minerals. Let's say they're anhydrous minerals. And so the melt's going to get richer in fluid until you basically get to the eutectic. And at this point, you're going to phase separate out a liquid. Now, the liquid is going to have a composition. The water is going to be saturated with silica, and the silicate melt's going to be saturated with water. And the structure of the silica in this system versus that system are very different. And so we would argue, based on all the compositional information I just showed you, that we would expect DH fractionation to occur between water here and water there. And then the problem is if your fluid started out, if you basically had a fairly fluid poor melt to begin with, it's going to, by the time you separate out these fluids, some will get out, but a lot will be trapped because it's an accumulate, and it's just simply not possible to get this stuff out. So you had to start with water in the mantle that presumably had some DH fractionation relative to the water that became the ocean. And that's interesting because a number of us are interested in what D to H means in relationship to SMO and to primitive materials in the solar system and even in the interstellar medium relative to the D to H ratio of the sun. And there are a number of different ways you can do this. In this particular case, some people like to mix a little bit of this with a little bit of that, and you can come right in the middle. And that's a very good explanation. However, we would argue that perhaps this DH partitioning phase also may add to that some degree of a signature that we do not yet appreciate. And there is evidence that the DH of the Earth's oceans have evolved over Earth's history, which is intriguing. So if that's the case, perhaps the Earth is slowly trying to homogenize what occurred or was set at the magma ocean phase of its existence. And my conclusions are that the detailed nature of water actually is much more complicated, I think, than many realize. And even though people have been studying this forever, and yes, it goes in as solenols or water, and now we know alkali hydroxyl groups, the simple fact of the matter is we really don't understand virtually any of the effects that I clearly showed you. I can't give you a physical explanation other than some arm wavy thing that I'm not going to waste your time on what's going on. So it's pretty still outstanding. This inconsistency that we just discovered, I actually discovered it with this. So when I looked at this disparity between the NMR and the FTIR, I was putting together the slides for this ATA talk. And when I saw that this behavior was completely, it wasn't doing anything like what people predicted from the sideband analysis, I thought to myself, I said, I don't think I'm going to show that slide. Let's let's think about this a little bit deeply. And now we're convinced that the data are fine. We don't understand where the physics could be wrong, but it might be. And we're doing experiments that will sort this out one way or the other. And we'll get there, at least to the point of confidence. Much more work needs to be done. Again, Ying Wang, Charles Lalas, Mike Ackerson, what makes being here so much fun is people come in and they want to do something, and you say, well, here's an interesting project, and off they go. I get to enjoy this because the nice thing about an NMR is that I'm the only person who knows how to run it. So I always get deeply into these problems because I have to basically do this. I always offer to teach people, but I said also, unless you're planning to buy one, I don't think it's a worthwhile use of your time to learn how to run it. And that's it. Thanks. I don't expect any questions. But I do appreciate you all coming. Yeah, Zach.
How do you figure out the SiOH content?
So the sideband analysis, you just simply say, well, if you've got 100% H2O and it's rigid, then the sideband intensities should be what they are. And then the fractional decrease relative to the center band is that amount of hydroxyl hydrogen, because it doesn't do dipolar. And this has actually been established by a guy way back when in static hydrogen NMR. His name is Burkhard Schmidt, and he would use, because the rigid hydrogen also has a strong dipolar interaction, it will also show a classic Pake powder pattern. So it turns out dipolar coupling hydrogen is quantum mechanically identical to a two-level quadrupolar system in terms of the Hamiltonians and how the physics turns out. It's kind of neat. But what we do is we spin. So by spinning really fast, you lose the classic Pake powder pattern associated with the dipolar coupling. All you have left is just this little rotational echo that propagates out in time. So it seems mysterious, but it's actually almost trivially simple. Yes? Mm-hmm. That's a great question. That was sorry, I did not put a proper attribution to that. So that was done. There are a couple of different ways of doing it, but that was done with ab initio calculations on cristobalite, and these authors made the argument that cristobalite would be the best model for this, and I don't know why, but that's their calculation. And how they did that calculation is, of course, in silico, they squashed the cristobalite. And so I went through their paper hoping that they would actually give me sort of effective pressures for each one of these points, because in principle you could do that. And then it would have been really cool, because I said, wow, you put potassium in there, and it's like you put it under 1 GPa or something, but you're holding it in your hand. But they didn't have that there, so I'd have to redo the calculations myself. Yeah, Larry.
So is that the only possible mechanism for
So in a very, very simple system, it is. So there's two mechanisms. One is you basically create a non-bridging oxygen, and that gives you a big shift. And then all the variation that you get within that little window that would define a Q2 or Q3, that's principally related to this. That's the predominant effect. So that's one of the benefits of having these super simple systems. When you get to a much more complicated system, if you put aluminum there, it will change the frequency quite substantially. And then you have to scratch your head and say, well, is that because the bond angles change, or is that because there's one aluminum or two aluminums? So I completely agree with Bjorn that it's good to keep it simple. But at the same token, I'm really enjoying working with Mike Ackerson because he's working with actual rhyolitic compositions. So you always want to bring it back to, yeah, but is this some stupid thing that the tetrasilicates do, or is there really some real-world application? We had to do the same thing when we identified the intermolecular DH fractionation. We synthesized a model basalt glass composition because we knew that Steve Shire, wake up, Steve, would never believe me if I did it just for sodium tetrasilicate, right? Because if it's sodium tetrasilicate, forget about it, right? Basalt, maybe you'll listen. So. Well, I'm done. So, thank you guys for coming.
Okay, yeah, me too.
Hello.
Really was.
It was fun to give.
No, really, I know